In the last lesson, we linked stats with the binomial distribution. Today, what we're going to look at is the normal distribution. So recall that when samples are taken from a large population, the values of the sample proportion after a while will look binomial. Okay, so remember p hat equals x on n, with that being the random variable, and we were using this formula here on it. So why does that happen again? Well, let's have a look at the Galton board and see how that works. Okay, so again with the Galton board, as the ball falls, it's got the chance of either going the left or the right, so success or fail. And each time we do this, if we do this enough times, what happens? We get the normal distribution curve, or the binomial distribution, which is approximated by the normal distribution curve. Here it goes again. The binomial distribution approximated by the normal distribution. It's not a perfect approximation, but it's pretty good. All right, so that is the link there. So from 16e, we know that when the sample size or the number of repetitions is relatively large, the distribution of a binomial random variable is well approximated. It's not perfect, but it's well approximated by the normal distribution. And it does depend on the proportion or probability under investigation, and must be large enough to so that we're likely to see at least 5 of each of the 2 possible responses or outcomes. I'll go into explain how we're going to do that. And it is ideally, this is a rule of thumb, but ideally at least 5 and ideally at least 10. Okay, so more than 10 is good. Because we know that if it's that number there, the curve that comes out will be roughly normal. Whereas if we don't do it enough times, okay, or the sample isn't large enough, then we're not going to get a normal distribution curve. Okay, so in summary, the normal curve approximation rule for sample proportions can be defined as follows. When the sample size n, or the relative number of repetitions, is large enough, that is NP, and n multiplied by 1 take p is at least 5, then the sample proportion has an approximately normal distribution with a mean of the population proportion and the standard deviation, which was the same standard deviation rule we saw in the last lesson. So let's have a look at this. Assume that 60% of girls in Catholic schools in Australia have a ribbon and in their hair. So that's the population proportion. Use your calculator to illustrate a possible distribution of the sample proportions that may be obtained when 200 different samples, each of size 25, are selected from the population. And are we even allowed to use the normal curve approximation? Well, I think we are. Okay, if we look at the size, so n is equal to 25, then we look at p is 0.6, so that's 6/10 times 25. Now what's that going to be? That is 2 and 5, that's 30 on 2, which is 15. Okay, and that is larger than 10, so that's okay. Then n equals 25, 1 take p equals 0.4, 4/10 of 25 equals 10, which is also okay. So ideally more than 5, or at least 5, and 10 is even better. So we are allowed to use a normal curve approximation. So what I'm about to do is just demonstrate this. You actually don't need to know how to do this, but you just need to kind of watch what happens next. So for the first time this year, we'll go to the spreadsheet. Okay, and what the spreadsheet allows us to do is to put a formula in. The formula I'm going to use is this one called rand binomial. Now rand binomial asks for 2 things. It's going to ask for what's it ask for first? The sample size, which is 25. I think this is the right order. And the chance of success, which is 0.6. Now what this will do is generate a possible sample from the 25. Let's just see. So it's 18. So 18 girls out of 25 wear a ribbon in their hair. That's a possibility. Now what we're going to do is do this 200 times. So the way we do this on the calculator, and again, you don't really need to know how to do this, is we fill range from A1 all the way to A200. This is going to do this experiment 200 times. And what we see is the possible sample sizes. Okay, so this is 14, this is 15, this is 13, 14, etc., etc. So we can see here these are all the possible ones. So this one here was 20 out of 25. All right, that's going to be more unusual. We know that that's more unusual. I wonder if there's any single figure ones. 11's pretty low. So 11 out of 25. Did we get any single figure ones? Unlikely. Alright, anyway, so I could look through this list all day, but what I want to do is actually go to the graph, and I'm going to get it to do a histogram of this data. Alright, not the world's greatest histogram. What's happened there? So let's just try that again. So I'm going to go graph and histogram. There we go. And we can see there that we've got a more typical normal looking curve. Okay. Now if I do this again, so let's just get it to do these calculations again. So I'm going to go edit and fill range and do it again. What it will do is generate a different set of numbers. Let's go to the graph and histogram, and again we get something that's roughly normal looking, and I can continue to do this and take 200 more samples, and we can assume that it's just reasonably well approximated by the normal curve. Now that we know that, let's apply it. Okay, so here's your first exam style question that allows this technique to happen. So it's known that 96% of train travellers on a certain route had a valid ticket. So that looks to be the population proportion. A sample of 500 travellers, n equals 500, is taken. For samples of 500 travellers, p hat is the random variable of the distribution of the sample proportions of travellers without a valid ticket. Okay, so recall that p hat is x on n is 500. And we're looking at without a valid ticket. So that means that the thing we're looking for is not 0.96, but it's actually 0.04. So that's what we're looking for in this case. Alrighty, so the way we're going to do that is and so we want to find the probability that the random variable or the sample proportion is less than or equal to 3 out of 100 when approximated by a normal distribution. So don't do the normal approximation unless you're told to do it specifically in the question. Now to do normal, right, let's just see if we remember how to do this. I'm going to go interactive, distribution, continuous and normal CDF because it's going to be less than or equal to, so we need a bunch of them, so I'm going to use CDF. Now what it does is it asks for a lower and an upper, and it needs a standard deviation and a mean. So I need to get the mean and the standard deviation. So the expected value of the sample proportion is just the population proportion. In this case, it's equal to 0.04. The standard deviation is equal to, now recall, it's just p times 1 take p. This is on your formula sheet over n. So I'm just going to punch in some numbers here. So it's going to be, the lower bound is going to be negative infinity. Where's infinity? There it is. The upper bound is 3 out of 100. The standard deviation, I don't know what that is yet, but the expected value or the mean is 0.04. So let's just calculate it at this point, knowing that that answer is wrong, because I've still got to get the standard deviation. Right, so let's calculate the standard deviation. So shift root, shift divide to get the fraction. 0.04 times 0.96 all over, what's the sample? 500. Alright, now that I've got my standard deviation, I'm going to grab it and paste it in here, get rid of the 1, and ask the question again, and it looks to be A. Okay, so the chance of getting a sample proportion less than 3 in 100 is this probability, roughly 12%. All right. The donut machine at South Melbourne Market has a probability of 0.03 of producing a donut without a hole in the middle. So that's going to be my population proportion. Okay, we know that basically 3 out of every 100 donuts produced don't have a hole in the middle. Don't know why. So if we take a sample of 1,000 donuts, is it safe to assume that we can apply the normal curve approximation rule? Well, absolutely. So 1,000 is going to be large enough to do that. Now, how can we prove it? So let's do n times p first of all. So 3 over 100 times 1,000, which equals 30. Okay, so that's okay. And then n times 1 take p is going to be 97 over 100 times 1,000, 9,700, which is also okay. Okay, so are we safe to assume? Yes, we can use normal approx. Okay, now remember in a VCAR exam you'll be told to use it. Unless you're told, assume that you're going to use binomial. Okay, but if you're told to use it, then go for it. So what's the approximate probability that the proportion of donuts without a hole will be between 0.02 and 0.04? So basically, what's the chance of being the sample being 2 out of 100 or 4 out of 100, noting that the expectation is 3 out of 100. Okay, so the way we're going to do this is we'll get the expected value. Expected value of the sample proportion is just the population proportion. I expect to get 3 out of 100, thanks. Alrighty, now let's get the standard deviation of the sample proportion, which is going to be 0.03 times 0.97 all over 1,000 square rooted. So I'll just edit this one up. Which is roughly 0.00539 ... Okay, so what we can see here, let's see if we can actually work out what it's going to roughly be. So I'm going to imagine this as a normal curve. Okay, so the way I'm going to draw it is it's got a mean of 0.03. And let's go, one standard deviation will be 0.035. Then another one will be roughly 0.4. So 0. What's it going to be? 25? Yeah. And then 0.2. Right, so that's 2 standard deviations to the left and right on the normal distribution curve, and we're looking for it to be 0.02 and 0.04. So this is going to be really, really close to 95%, 0.95. So we should get roughly 0.95 when we do this. Now let's go and grab an old version of this. So what we're going to do is ask normal CDF to count up all the probabilities between 2 over 100 and 4 over 100, where our standard deviation is not that one, but it's this one, and our chance of success is 0.03. Right, so this should be really close to 95%. Okay, it's not perfect because this isn't exactly normally distributed. It's approximated by the normal distribution. So it is this value here. So in your notes, what I suggest is you note down what we've just put in. So it's normal CDF 0.02, 0.03. What was the standard dev? 0.00539 dot dot dot, comma 0.03 equals 0.9362 dot dot dot. They usually ask for 4 decimal places. All right, let's do C. What is the approximate probability that the proportion of donuts without a hole will be between 0.02 and 0.04, given that we know it is greater than 0.03? So this is conditional. Right, so again, let's just see what the curve suggests we're going to get. So we know that it's greater than 0.03. So it's all of these values here. So that, if it's greater than 0.03, we know that that's 0.5. Okay, so the probability that it's above the mean is going to be a half. And so we know that it can't be between 0.02 and 0.03 because they've told us it's larger than that. So it's the probability that it's between 0.03 and 0.04. So that's this part here. So the answer is going to be exactly the same as this one here. Okay, I know that the answer is going to be exactly the same, but you may not see that yourself, so I'm just going to work it out for you. So this one is going to be let's do it via normal CDF. So I'm going to get the probability that it's between 0.03 and 0.04 with those parameters. And I'm also going to do this again. And that's going to be above 0.3 to, this time, positive infinity. That one's going to be 0.5. Where's infinity? There. Okay, so that's 0.5. So it's going to be that over the smaller sample space, which is exactly the same number. So this one here, C, is exactly the same as B. 0.9362 dot dot dot, because of the graph above. Okay, the graph above tells me that that is going to be equal. All right, let's do another one. Sasha is shooting at a target which she has a probability of 0.6 hitting. So P is equal to 0.6. What's the approximate probability that the proportion of times she hits the target in her next 100 attempts is 8 out of 10? All right, well, let's do this. So we're assuming here, so let's assume normal is okay. Now, I wouldn't usually assume that normal is okay. I'd typically do binomial on this, but because this is the 17C chapter, I'm assuming that normal is okay. Again, in a VCAR exam, you'll be told that a normal approximation is expected. All right, so how are we going to do this? We need to recall that the expected sample proportion is the population proportion, which is going to be 0.6 in this case. The standard dev is going to be 0.6 times 0.4 over how many times is she doing it? 100 times. Okay. All right, so let's just again get a little bit of a visual on this. So 0.6. Now one standard deviation to the left and right is 0.64, 0.56, 2 standard deviations is 0.68. Alright, now this first question, the proportion of times she hits the target in her next 100 attempts is less than 0.8. So 0.8 is going to be all the way up here. So less than 0.8 means all of these added together. So it's got to be almost certain. So let's just write down our calculation. So I'm going to use normal CDF. My lower bound is negative infinity. My upper bound is 0.8. What do we give first? We give the standard deviation first. So 0.0489. And the mean is 0.6. Right, so again, I'm expecting something extremely high. The chance is extremely high according to the picture. Come on, down you go. Okay, so we've got negative infinity there. And 0.8. Standard dev, that's in the answer slot, so I'll just use A and S, and 0.6. So again, expecting, yep, there we go. So to 4 decimal places, it's 1, it's certain. Okay, and the reason for that is like 0.8 is more than 3 standard deviations above the mean. So it's certain. Okay, let's do B. So this is going to be norm CDF is between 0.6 and 0.8. So this is going to be 50%. Yeah. Okay, 0.5. And we can see that because here's 0.6 and 3 standard deviations is above there, the area is going to be half. Okay, what's the proportion of times she hits the target in her next 100 attempts between 0.7? So 0.7 is up here and 0.8, given that it's more than 0.6. Right, so this is going to be, so the chance is going to be, is it high or low? So we know that this is going to be a low chance because the probabilities between 0.7, which is here, and 0.8, that's a small amount over half of it. So it's going to be a really small probability here. So the way we're going to do this is, for part C, we're going to do normal CDF, and we're going to get the prob between 0.7 and 0.8 for this standard deviation, and that's success. And we're going to divide that by normal CDF, 0.6 to positive infinity, 0.0489 ... and 0.6. Apologies for running out of room. Alright, so let's rip that one, change that to 0.7, 0.8, pop the standard dev in there. Okay, so that's the small probability divided by, I mean, I could just put in 0.5. I'll put it in properly because I'm worried about the rounding. So 0.6 to positive infinity. That's not right. Yeah, of course it's not right. I was expecting that to come out as 0.5, but I've actually just divided that. So that's our actual answer. So it's a small probability. In fact, it's 0.04118 depending on the number of decimal places. So that's that one. So I think with these questions here, it's a really good idea to kind of know what's going to happen by quickly drawing a normal distribution curve and expecting an answer rather than going, oh, okay, well, I suppose the probability is that. Right, so the last question. Given approximately 85% of Australians are right-handed, what's the probability that in a sample of 200 Australians, from 160 to 170 people are right-handed? Okay. Right, so I remember this one from a few years ago because there was this note in Mr. Tench's question. An inclusive integer interval is approximated from the point 0.5 outside the interval. Okay, so it's from 160 to 170, so that means we want these. All right, now in the previous question, we were looking at between values, so between 0.6, less than 0.8, whereas this one's looking at it equaling or being 160 itself to 170. So when we include values, what we do is we use, I think it's called the continuity correction factor, right? Something like that, where what we do is we look for the probability or we add 0.5 to each of these. So we're actually going to find from 159.5 to 170.5. We're going to make a slight correction when we do this to allow for when we get sort of like the areas to include those values. Because it doesn't include it itself, we just stretch it out a little bit further so that we get the 170 and the 160 included. All right, so to do this, we are going to get the expected value, which is obviously 0.85. It's the population proportion, and the standard dev is going to be shift that 0.85 times 0.15 all over, how many are we doing? 200. 0.025 ... Okay, so what we'll do is we'll plug, so we'll use normal CDF. Now our lower bound is 159.5. Now remember this is the sample proportion, so it's 159.5 over 200. Then the upper is going to be 170.5 over 200. The standard dev 0.025 ... and the expected value, that. All right, so let's fire away. Interactive. The lower 159.5 over 200. Uh, 170.5. Standard dev, I'll just leave that as 1 at the moment. 0.85 is the expectation. And then what I'll do is grab the standard dev from the previous line, get rid of the 1. ... 4 decimal places in the exam. Alright, so there you go. So in 17C, assume that you're allowed to do the normal approximation and go for it.